Okay, good morning. Here we are. It is, once again, the video lecture, Physics 105B video lecture 10. Okay, we're in the middle of some great material, and we ended up with the Euler-Lagrange equations for a many degrees of freedom system. Small oscillations with many degrees of freedom. There we go. Yeah, so let's write down what we have in the various definitions. So this is small oscillations for systems with many degrees of freedom. I'll even draw a little one-dimensional Q sub 0. Okay. In honor of the whole multivariable version. Yeah, we started with a Lagrangian of the general form, and I'll write this here, Ij Qi dot Qj dot minus U of Q, and we had an stable equilibrium at Q sub 0, and we made our way through this, and we ended up with the following equation. So I'll showcase this pretty large. We had sum over Mij xj second derivative plus Kij xj equals 0. We were summing over j equals 1 to n, and we had I equals 1 to n. So those are coupled equations. Everything here is under the sign. And I think I ended by pointing out that if n is equal to 1, we just have the simple harmonic oscillator. So let's put a box around here. Now the nice thing about this theory is, although it has that nice compact form, there are some things hidden away in here. So the Mij matrix of constants is actually Aij evaluated at Q sub 0. Okay. These were functions, you didn't want to differentiate them, but evaluate them at Q sub 0. The K sub Ij matrix was the second partial Qi Qj evaluated at Q sub 0. And then the X sub I is the Q sub I minus Q sub I 0. Okay, so small oscillations. And you know, we just chose these letters in honor of the mass and the spring constant. They're not masses, and they're not necessarily spring constants. Okay, the second derivatives. Good. Now, we're going to solve this thing, but the first thing we have to note about it is the form. This is a matrix multiplication. So let's just make sure we see that. Note that this equation star right here is a matrix multiplication. So what do we mean by that? Since we're summing over the j, it's as though we had the ith row of this matrix times the column. Okay, the ith row times the column, we're summing over j. So if we let M be equal to this Mij matrix, I'm just saying this is the square matrix, and K be equal to this square matrix, then we can explicitly write, and x be this x1 down to xn. Think of that as a column vector. Then each one of these equations is a row times a column for the differential equation. Matrix times vector equals 0. How about that? So apparently we're going to need some of our linear algebra. Okay, so as a matrix equation, system of coupled linear differential equations with constant coefficients. Let's go ahead and write that down as well. System of linear differential equations with constant coefficients, and that is something for which there's a well-developed solution theory, constant coefficients. Good. I'll probably say a couple more things about this for completeness. These matrices can always be made symmetric. Okay? Matrices are symmetric, and these are they came out of quadratic forms, positive definite quadratic forms. Okay. Good. So I think we had that terminology last time. I'll just put this here as a note as well. Mij, Kij are symmetric. We can always make them symmetric. I'll show you that in a particular example later on. Symmetric, and the quadratic forms that go with them are positive definite quadratic forms. Sum of Mij, or let's write this for K as the general case. Sum of Ij, Kij, Xi, Xj, positive definite. Positive definite quadratic form. Good. So what we're going to do is solve this and get the general case solution. And then we'll go ahead and, so yeah, this is all very theoretical. Then we'll look at the concrete examples. I'll bring a model in, coupled oscillators, coupled pendula, and interesting stuff like that. So right now we're just looking at the general solution theory of this. Okay. It has to be done. So to solve this thing up here, which is equivalently this thing right here, we're going to let x sub I be equal to, or I could say x sub j. X sub j be equal to a sub j e to the I omega t. So that's a trial solution. That's the general solution, and that's because the general solution to this linear differential equation with constant coefficients is an exponential. Okay, generally speaking, complex. This is actually going to be real, and we'll prove it later. On general principles, we already know that this omega has to come out real, otherwise we would have damping or anti-damping, which is to say, if omega is not real, then we're going to have a violation of energy conservation. But we'll prove that rigorously next time. We're just going to go ahead and plug this in now. So we let this, and then we go ahead in there, and we've got our sum, j equals 1 to n. We're going to take two derivatives. So we're going to have mij, xj second derivative, so that brings down I omega squared aj e to the I omega t. Did a lot of this last semester. Still under the same sign. Kij aj e to the I omega t equals 0 for some minus omega squared mij aj plus kij aj and then we would have e to the I omega t. Yeah, I'll go ahead and do this and then we'll write it out one more time. Okay, this is never 0. So we can actually pull that off, common to the whole row. And this aj is common right there. So what this brings us to is minus omega squared mij plus kij parentheses a sub j equals 1 to n equals 0. Okay, so now what does this look like? It's got that same matrix multiplication structure we were talking about before. So if I want to write this as a matrix equation, I have minus omega m plus k times the vector A equals 0. Okay. And this reminds you of the eigenvalue, eigenvector problem that we've studied before, except typically we would have a diagonal unit matrix here. Okay. But now we don't. We have a square matrix here as well, but the basic linear algebra still holds true. Namely, we're only going to get a non-trivial solution to this equation if this matrix, take this entire thing in parentheses as a matrix, if this matrix has some linearly dependent rows or columns. Okay? That's the only way we're going to get a non-trivial solution to this. That is to say, a solution where A is simply not 0. So the condition on this is that the determinant of this matrix minus omega squared m plus k vanish. So here, only non-trivial solution if this holds true. So there's our criterion. We're almost done. So now we have everything on the board. We would have to start with our mechanical problem, find out all these quantities. Whether or not you write them down as a matrix, they are, they form a matrix. So these were out of the physics here. And now this determinant is a polynomial in omega squared. It's an nth order polynomial, nth degree polynomial in omega squared. And that is called the characteristic polynomial. Yeah, I want to get it all on one board, huh? 2 boards. So I've got a little bit of room right here. So it's an eigenvalue, eigenvector problem. The eigenvalues are these omega squareds. They are positive and real. I'll prove that they have to be later. On physical grounds, we can argue that they're going to be positive and real. And then if you can find the eigenvalue, you can go back and find the eigenvector. Okay, they're both going to have physical significance. The eigenvalue is an oscillation frequency, or the square root of that eigenvalue is an oscillation frequency, because we started with, right there, we started with this here. How about blue? And And we know if there's no complex omega here, you know, I omega is just the oscillatory trigonometric function. Good, so I'm going to go ahead and write that out here, what I just mentioned to finish this up. So omega squared are eigenvalues and the vectors A are corresponding eigenvectors. So these eigenvalues here are called characteristic frequencies. And what the eigenvectors are, we'll get into later as well. Okay. Next thing we have to do is an example of this. This is beautiful. Okay. So eigenvalues, all right, it's an eigenvalue eigenvector problem. So we're going to do both. Okay, so the system I'm going to show you two-by-two system. You know, as long as there's no more than 2 degrees of freedom, we know we can nail this. Okay. 3 degrees of freedom, determinants, you know, 3x3 determinants, not so fun, right? 4, 5, 6, it gets worse. But 2 coupled oscillations, not only do we have the theory, but we can get any solution we want, or any system we want. Yeah, let's see how we're doing here. Good. All right, so I'm going to erase all of this, and so let's look at the really prototypical system of coupled oscillators. Example is, of course, we got a frictionless system. So here's our x-axis, and what we're going to do is have a mass on a spring, make this nicer, and have a mass on a spring. There's a mass m, spring constant k. And then we're going to connect it with an ideal spring to another mass, equal mass m, a different spring constant. We're just going to name it k prime, and then we'll have a third spring over here and block it off. Okay, so there's a certain symmetry to this thing. 2 equal masses, 2 equal springs on the outside, and this is the one that couples them together. And depending on the value of k prime with respect to k, we can get different phenomena. So what we'll do is we'll call this the position x1 and x2 equals 0 at equilibrium when the springs are relaxed. So there's our example. And I'm going to write or here because this is not the one I can demonstrate to you in class. But if you want to build a system with these properties, you take 2 pendula of equal mass and length, okay, and then you couple them with we couple them with any kind of spring you want. And getting ahead of the game, we're going to couple them with a weak spring. And this is the system that we actually have here in the department. We had a couple of these built. So then you would have M, L, M, L, and maybe some spring constant K here. And you hang them from a frame, and then if the spring is 0, then they just oscillate independently like pendula. But this is a realization of this idea. This is the one we're going to calculate initially. But I'll put a homework up here right now. and that will be to construct the Lagrangian. In fact, I have to be a little more precise here. So just to make the construction of the Lagrangian easy enough, we'll put the little spring right in there, call that K. So homework, construct L for this system, and you can see it's going to be L of theta 1, theta 2, theta 1 dot, theta 2 dot. And I suppose I have to have a separation distance d here built in. So yeah, we're going to construct the Lagrangian for this and make sure that it's equivalent to the Lagrangian for this. And I'll make that more clear and show its equivalence to L of the system star right here. In the case of small oscillations, it's definitely not equivalent in the general case, but for small oscillations it is. Small oscillations, okay. So that's a great problem. Equivalence, what does equivalence mean here? The two Lagrangians will be equivalent if you can just map one onto the other by renaming the coefficients. Because this one's going to have, you could say it would have moments of inertia in there effectively. Whereas this one's linear, okay? But you'll be able to make a substitution of the coefficients from one to the other. This one here is going to be L of x1, x2, x1 dot, x2 dot, okay? So it'll be theta 1, theta 2, theta 1 dot, theta 2 dot. So if you can just obtain one from the other by relabeling the coefficients, then you know that if you've solved this one, then you know the answer to this problem here, just by renaming the coefficients. Okay, so that's what equivalence means, and let's go ahead and tackle this thing now. And by the way, this is the one I'm going to bring into class and demonstrate to you. Very interesting problem. Okay, so we want this Lagrangian, and here is how it goes. The kinetic energy is just a half m x1 dot squared plus a half m x2 dot squared. Okay, that's done. But the potential energy is interesting. For a system like this, the potential energy is stored in the spring. It's a massless ideal spring. That's where the potential energy is stored in. So here's how we build it up. In the first spring there will be a half k x1 squared. Because x1 is here, this is x1 equals 0, so this one moves a little bit. That spring's being stretched, okay? And we'll have the same on the right side, a half k x2 squared. And that's when this mass moves, okay? But what about the energy stored in the middle spring? So this is the key one to pay attention to. It's a half k prime, and then it's the difference between x1 and x2, okay? So if x1 and x2 move together, then there would be no energy stored in the spring, okay? But if they move opposite or apart from each other, then there will be energy stored. So it's the difference, x1 minus x2, the quantity squared. So this is what we're going to use to turn into our turn this into our Lagrangian. And you could say, from the standpoint of the original theory we had up here, we already took our derivatives and found k. Okay. found these are the second derivatives, so that's what these spring constants mean. So that step was already done, and we have this ideal system, and now we have kinetic and potential. So now we want to put it into that standard form and obtain these matrices here. So that's the next thing. And for pedagogical reasons, I'm not going to just go to these coefficients, but I want to take it through the small oscillations Lagrangian. So L small oscillations is half m x1 dot squared half m x2 dot squared. And now the potential energy, I'll pull that, that's not a good bracket. I'll pull that, keep the minus sign out front here. So here's what we're looking for. When we multiply all this out, we are looking for 1/2 times something x1 squared plus 1/2 x1 x2 plus 1/2 times something x2 x1. This is the one we're going to put in by hand. This is that bookkeeping I was telling you about, 1/2 x2 x2, so x2 squared. So yeah, what fills these things here? Well, we have x1 squared from here and an x1 squared from there. Okay, so that'll be 1/2 k plus k prime. Okay. And then for the x2 squared, we'll have half k x2 squared and x2 minus x2 squared. So again, we're going to have k plus k prime here. Now we just have so we've gotten rid of those. We have a cross term minus 2k prime x1 x2. Okay. The cross terms here, we've got 1/2 times -2 k prime x1 x2. So what we're doing is we're splitting up those cross terms and putting part of it here and part of it there. So that's why we have that minus k prime in both of these, okay, because there were two of them. Right. We always pull the 1/2 out front, okay, so then we populate these matrix elements like that. So we got the minus k prime twice. And that's what I meant by always being able to make that matrix symmetric. We could have, of course, had 2 k primes here and none there, but we want the matrix to be symmetric. Okay, so now we can get our matrices. The matrix M is just equal to M, 0, 0, M. Okay. 1, 1, 2, 2, and the cross terms don't exist on this system. On other systems they do, by the way. What about the matrix K? Kij. So you see we have K plus K prime from here, minus K prime, minus K prime, and then K plus K prime right here. So you see, you don't, strictly speaking, have to write out the small oscillations Lagrangian, but we're going to want to do it a few times just to make sure we see what's going on here. This is what we were after. And now to find the eigenvalues, next, to find eigenvalues, we're making this minus omega squared m plus k determinant equals 0. So now let's do that. Determinant minus omega squared m plus k equals 0. So minus, let's write out this matrix. In fact, I'll write it out the word. In fact, so the minus omega squared m plus k, that's minus omega squared m plus k prime. Okay. and then we have minus k prime on the corners, on the off diagonals. And same thing here, minus omega squared m plus k prime. So now we take this 2 by 2 determinant, and that will be the characteristic polynomial. Now here's a warning. We've got this omega squared, and we don't want to actually multiply it out. Well, let's go ahead and just do this. So we have minus omega squared m plus k prime squared minus k prime squared equals 0. Now, once you have the characteristic polynomial, even in this form here, you don't want to just multiply everything out because you could possibly make things worse. So at this stage of the game, you want to study this thing and find the best way to obtain your solution. Okay? You don't just go to town and expand everything out. In this case, for example, we can bring this over to the right side, take the square root of both sides. Okay? Save us a lot of trouble if we multiply this out. We wouldn't be happy. So, let's go ahead and do that. Boy, I'd love to have all these pictures up here. Well, we'll redraw them. Yeah. Okay, yeah, this one that I just erased we'll come back to later anyway. Okay, now what we can say is, just bringing this to the right side and taking the square root of both sides, I end up with minus omega squared m plus k prime is equal to plus or minus k prime. So those are my two solutions right there with the plus and the minus sign. So for positive sign, okay, plus k prime and plus k prime are going to cancel for both sides, and I'm going to have omega squared is equal to k over m. I could put a little plus here, or 1 or 2 later on, but that's that solution. For the minus sign, I'll have k, and then if I bring this together with the other one, I'll have 2k prime. So I'm going to end up with omega minus squared is equal to k plus 2k prime over m. And these we're going to study now because we've finally come to a solution where we can discuss the physical significance of these. So k over m and k plus 2k prime over m. So this second frequency, 2 didn't look so good. The second frequency here is slightly larger than the first. And let's start talking the physical ramifications. In the limit as that k prime spring gets weaker and weaker, the two frequencies become the same. And because those were identical oscillators, that's no surprise. Yeah, let me, I have to draw this system again. So, okay, let's do this. We have x-axis, we have one mass, m, we have a second mass, n, and those are the springs are fixed right there. x1, x2. K, K prime, K. Well, let's ponder this thing. By the way, this system, we could have actually, just by pure thought alone, we could have gotten these answers, but that's usually not the case. And I'll show you how. Because we know that this is just the frequency of an ordinary oscillator. So what this frequency is referring to is if these two masses were to move together, okay, and this massless spring were not involved, okay, that would be the frequency of the motion of the two masses together in phase. This here is the frequency of the two masses moving against each other, okay, out of phase. And in fact, this 2 times K prime, make that a little cleaner, this 2 times K prime is explained by the fact that if you cut an ideal spring in half, you obtain twice the spring constant. I'm thinking we assigned that last semester, but that's something you can figure out and prove if you haven't shown it before. You take an ideal spring, this is a really simple calculation. Take an ideal spring and take half of it, and you effectively get twice the spring constant. So that's where that 2 comes from. So that's as though you were to nail down this thing in the middle, have them going across each other. So here's the thing. Did I just make that up? Or how would we mathematically prove that this frequency goes with that motion? And the answer is we would inspect the corresponding eigenvectors. Corresponding eigenvectors can be used to construct what are called normal modes. Okay? And these would be the 2 normal modes. And the corresponding eigenvector for this eigenfrequency is going to be 1, 1, which means that x1 and x2 move in concert in phase, and the other eigenvector is going to be 1 minus 1. So let's add this to the homework as well. Show that the corresponding eigenvectors are 1, 1. You don't have to normalize them. And 1 minus 1. Yeah. And this eigenvector goes with this right here. So this is the plus. And this is the minus. All right. So yeah, this system is one that's going to keep on giving, because everything that happens here is completely transparent. Whereas more complicated systems, you can calculate the things, but you can't just see that they're true like we can on this one. Okay, let's see how our time is running. Okay, that's not bad. So we have a couple of interesting problems to do. Let me come back to that discussion of the pendulum system. So yeah, once you find these eigenvectors, we'll have everything in place to start talking about normal modes. But this pendulum system, coupled pendula, let me go ahead and draw this again and get us started on that. So we want the Lagrangian, same mass, some little spring constant K, some separation distance D here, just in case we need it. Okay. So it's symmetric here. So what is the kinetic energy? You're going to find 1/2. Now, you don't explicitly have to go into plane polar coordinates, but you can. But you know, this is going to be a θ1, and this is going to be a θ2. So you're going to have 1/2 m, and then L theta 1 dot squared. Or you can say 1/2 ML squared theta 1 dot squared. And the same thing, ML squared theta 2 dot squared. Right, now if you compare that to this, you can say, okay, I can make my replacement x and theta, x1 and theta 1, x2 and theta, and then I can rename my m ml squared. So the kinetic energy clearly has the same form. And what that mass, so not mass, but that so-called m is going to look like, matrix is going to look like ml squared 0, 0, ml squared. So if it just came down to the kinetic energy, this is what I mean by them being equivalent, right? This matrix and this matrix is just rename those coefficients. Now what about the potential energy? I'm going to erase this here and construct and look at the potential energy. Now remember, the potential energy is just gravitational as well as elastic with that spring there. So the potential energy, the gravitational part is minus mgl cos theta 1 and minus mgl cos theta 2. Pretty sure we've done pendulum before, right? Potential energy of the pendulum. I hope so. But yes, it is, because this is just comes from mgy. Now, we have that plus apparently 1/2 k times what? The separation distance of these things squared. So I'm just going to name that R12 squared for the moment. Okay. So this looks nothing like that up there, right? But what would we do? We would take the small angle approximation, small angles, and if you do the small angles, cos theta without the subscript, just cos theta goes as 1 minus theta squared over 2. You're going to inherit some constants that you can throw out of your Lagrangian. And then this R12, for small angles, it's essentially just separation distance along the horizontal. So you can do away with the idea that you got to do some Pythagorean theorem here because of the different angles. Okay, for small oscillations, it's essentially just along the horizontal. Yeah, but when you do that, you can already see now we're going to be able to populate these things, and we'll end up with theta 1 squared, theta 1, theta 2, 2, 1, theta 2 squared. This one's a little bit of a challenge, but not too bad. And then once you get something where you just have that theta 1 squared, theta 1, theta 2, theta 2 squared with the relevant coefficients, you'll see that you can rename. This K is going to be a little more interesting. This one was pretty trivial. But you'll be able to rename them so that one maps onto the other, and then they are equivalent. So everything we will learn about this system, we're not done with it yet, will then apply to the small oscillations of this system. Good, so I think that's enough for today. Yeah, very well. Good, so see everybody next time, and enjoy this.